I like problems like this because they're simple to state. Point on the plane x minus y plus z equals 2 closest to the point 1, 1, 1. And guys, I always check. Is the point on the plane? Not quite. 1 minus 1 is 0 plus z is 1. Oh, so they're 1 apart. No. Right? I mean, if only it were that simple, right? Although if you think about it, look, maybe the answer is 2 comma 1 comma 1. Right? That's on the plane. That's on the plane. Or 1 comma 0 comma 1. Then you get to write 1 plus 1 is 2, and you don't get to do that in Calc 3 class very often. Well, okay, so here's my guess, just for fun. Let's see if it's right. I doubt it. All right, so what do? Well, we want to, again, maximize, no, closest, minimize what? The distance. I'll call it d of x, y, z equal to, I remember the first time I taught Calc 3, we had time to prove this, and it was so fun. X minus, well, 1 squared plus y minus 1 squared. See, the distance formula generalizes to 3 dimensions. There it is, right? x2 minus x1 squared, y2 minus y1 squared, z2 minus z1 squared. Add them together, take the square root, and that's the distance formula. Oh, subject to the constraint. What's the constraint? It has to be in the plane. So, see this thing here? That, right? I'll just call that asterisk. I don't have to write so much. Okay?
We have to set that equal to 0, correct?
Well, I guess if I'm going to do Lagrange multipliers, I'll set it equal to 0. If I'm going to do it the 14.8 way we're on now, then I'll solve for something and plug in. But before I do any of this, I'm going to give you guys a huge hint about problems like this, which I was talking to Sullivan about here just a minute ago. It is easier to minimize the following function, f, which is d squared, which is just this function.
Or in Calc 1, you just said we can just minimize what's under the square root and we don't even care.
That's what I just said.
Oh, yeah, yeah. But you never said d squared.
Well, that's because you were in Calc
Yeah,
1
I
and you
know.
would have got scared. What's he doing?
Yeah, okay.
But see, now you're in Calc 3. We could be more mature, and we're gonna minimize this. And then the fact is, if I minimize this, I minimize the distance. Now, why is that true? Calc 1 doesn't remember that usually. But let me show you why. Well, let's show you why it's logical. D of x, if I were to graph it, I claim it looks something like, although it's funny, I just called it d of x, but it's not x, it's x, y, z, right? Okay, you got me. D of, who cares? Pretend it's just one variable. Let me call it v. Pretend that for a minute. Can I really do that? Well, then it's the square root of stuff, right? What's a square root function look like in general? It looks like this. It's like starts at 0 and goes this way, right? It's an increasing function. Is that true? It's always increasing? You could prove that, right? You could take the derivative. You'd see the derivative is always positive. Or do you just know the graph really well, which you also do? And so since it's an increasing function, if I want to maximize a square root function, all I have to do is maximize v, the x direction. And so that kind of proves this. If you need a little more detail, that's fine, but hopefully that's enough. To give you a ballpark figure, this picture kind of shows why it's true. Okay, so let's minimize this thing. How do we minimize this thing? Well, okay, I like your idea. I think Jesse said let's solve for z in the constraint, right? So let me do that. I'll take the constraint. So the constraint can be rewritten as z equals, I guess it would be, well, 2 minus x plus y, right? That's a way to rewrite the constraint. And then I'll come over here, and what I'll do now is I will minimize. Now I want to write f as a function of x and y. F of xy is equal to x minus 1 squared plus y minus 1 squared. And then here, this z will replace it with this. Well, there's the 2, right? So 2 minus 1 is 1. So plus, I guess it would be 1 minus x plus y quantity squared. There's f of xy. Okay so far? Let's compute a couple of partial derivatives. The x partial, I get 2 times x minus 1 plus 0 plus 2 times 1 minus x plus y to the first power, times what? Negative 1. Let's put that negative in pink here so I don't forget it, right? So instead of plus negative, I probably should have written minus, but I wasn't planning ahead. Here we go. Fy is 2 times y minus 1 times 1 plus 2 times 1 minus x plus y times 1 this time. So there they are. Okay. Next step. Sure, we want to find a critical value. Let's set them equal to 0. Here we go. Let's see.
Yeah.
Sullivan, is this easier than the algebra you did, by the way?
Yeah,
Oh.
I never even
Okay.
eliminated a variable. It got really messy.
I believe it. And then this is minus 2y equals 0. And then I'm just distributing right now. I kind of tend not to talk this out. Let me just kind of work on it a little. I noticed the bottom equation is a little nicer because the 2's go away. I have negative 2x plus 4y is equal to 0. That's really nice. The top equation, I could set it equal to 4. What is it that equals 4? Is it 4x minus 2y? Yeah, you know, this algebra is not too bad. I mean, it's all relative, of course, right?
Yeah, that's the system I got at the very end.
Me too. Hey, nice work. So let's see. I guess I get from the bottom equation, 4y is 2x, so y is 1/2 x. And when I plug that into the first equation, I get 4x. Since y is 1/2 x, it's just minus x is 4. 3x is 4. X is 4/3. Must be y is 2/3. And then z, right? So we can answer the question. Find the point on the plane closest to 1, 1, 1. It would be 4/3, 2/3, and then to get the z value, I guess I better write the original equation down. It was x minus y plus z has to equal 2. Oh, no, I solved for z already. I had z was equal to 2 minus x plus y, so I could just get it that way, right? And so I get z is equal to 2 minus 4/3 plus 2/3. So 6/3 minus 4/3 is 2/3 plus 2/3. You guys get 4/3? How's that look? Doable?